In this chapter, we are going to look at how BIM is used differently across the project life cycle. One important idea to remember is that BIM is not just software, and it is not just a 3D model. BIM is a project workflow. Its value comes from using the right model information at the right time for the right purpose. For example, during the planning phase, BIM may support feasibility studies and massing studies. At this stage, the model does not need to include detailed building systems. The purpose is to help the team explore early options and understand whether the project is feasible. During the design phase, BIM becomes more useful for coordination and clash prevention. Architects, structural engineers, and MEP engineers can use their models together to identify conflicts before construction begins. During construction, BIM supports sequencing, constructability review, and field coordination. The team is no longer just asking, "Does the design work?" They are asking, "How will this actually be built?" Finally, during operations, BIM can support asset information, maintenance planning, and facility management. So, the key message of this slide is that BIM uses should change by project phase. A useful BIM strategy is not about using every BIM function at once. It is about selecting the BIM uses that provide the most value at each stage of the project. During the design phase, one of the most important BIM uses is design coordination. On a construction project, architects, structural engineers, and MEP engineers each develop their own models. These models contain different types of information, but they all have to work together in the actual building. This is where a federated model becomes important. A federated model brings separate discipline models together into one shared coordination environment. It does not replace the individual models. Instead, it allows the project team to see how the systems interact before field installation begins. This is where a federated model becomes important. A federated model brings separate discipline models together into one shared coordination environment. It does not replace the individual models. Instead, it allows the project team to see how the systems interact before field installation begins. There are two common types of clashes. A hard clash happens when two physical elements occupy the same space. For example, a duct may run directly through a beam. A soft clash is different. In a soft clash, the elements may not physically overlap, but there is not enough clearance for access, insulation, maintenance, or safety. However, the goal of design phase BIM is not simply to detect clashes. The real goal is to prevent them. Through coordination meetings, the project team can decide how systems should be routed and which systems should take priority. When conflicts are resolved before construction, the project can reduce rework, RFIs, change orders, and schedule delays. That is why BIM coordination during design has such a direct impact on constructability. Once the project moves into construction, BIM begins to support field execution more directly. At this stage, the project team needs to understand not only what will be built, but also how and when it will be built. This is where 4D BIM becomes useful. 4D BIM links the 3D model to the project schedule. The fourth dimension is time. Instead of showing only the completed building, a 4D model shows the sequence of construction activities over time. This visual sequence helps construction managers, trade partners, and field teams understand the planned order of work. For example, they can see when foundations, structural framing, enclosure systems, MEP rough-in, and finishes are expected to occur. One benefit of 4D BIM is site logistics planning. The team can review crane locations, laydown areas, material delivery routes, worker access, and equipment movement. On a crowded site, these issues can strongly affect safety and productivity. Another benefit is the ability to identify temporal clashes. A temporal clash occurs when two activities are scheduled to use the same space at the same time. If the team identifies these problems early, they can adjust the sequence before the conflict affects field productivity. BIM also supports constructability review. Constructability review asks whether the design can actually be built under real conditions. Contractors and trade specialists can use the model to review installation access, sequencing, temporary work, and system routing. So, in the construction phase, BIM helps bridge the gap between design intent and field reality. It gives the project team a clearer way to plan, communicate, and execute the work. This slide introduces one of the most important lessons in BIM management. More BIM does not always mean better BIM. The Penn State BIM Guide identifies more than 25 BIM uses across planning, design, construction, and operations. However, a project does not need to use all of them at the same time. In fact, trying to use every BIM function at once can create problems. The model may become too large, too slow, and too difficult to manage. It may include information that is not reliable yet, or information that is not needed for the current phase. This is what the slide refers to as pseudo-BIM. It may look advanced because many BIM functions are included, but it does not actually improve decision-making. Instead, it creates overload and waste. A better approach is selective BIM application by phase. This means the project team chooses the BIM uses that support specific decisions or tasks at each phase. The phrase model for use is very important here. The model should include information because it supports a real project need, not simply because the software allows it. For example, during planning, the team may focus on massing and feasibility. During design, the focus may shift to 3D coordination and clash prevention. During construction, the focus may shift again to 4D scheduling, logistics, and constructability review. These selected BIM uses should be documented in the BIM Execution Plan, or BEP. The BEP helps clarify what the model is for, who is responsible for each use, and when certain information should be developed. The key takeaway is that a lean, focused model is often more valuable than a large, overloaded model. Selective BIM helps reduce waste, improve performance, and increase return on investment. This case study shows why selective BIM application is so important in real projects. The project was a complex hospital in the United States. Hospitals are very difficult buildings to coordinate because they contain dense networks of HVAC systems, plumbing systems, electrical systems, medical gas piping, and specialized equipment. Many of these systems must fit within limited ceiling and wall spaces. At the beginning of the project, the owner required full BIM from schematic design onward. The team was expected to use 3D coordination, 4D scheduling, 5D cost estimating, and facility management data integration very early in the project. At first, this sounded comprehensive, but in practice, it created serious problems. The model became overloaded with information that was not useful yet. For example, the design team was asked to enter facility management data before the designs and equipment selections were stable. As a result, the model became slow and difficult to use, clash detection produced false positive clashes, and coordination meetings became less productive. Instead of solving real spatial conflicts, the team spent too much time discussing data entry responsibilities. The general contractor's BIM director then changed the strategy. The BIM execution plan was rewritten to separate BIM uses by phase. During design, the team focused mainly on 3D coordination and clash prevention. This allowed the MEP subcontractors to concentrate on routing major systems efficiently. The team also used a coordination hierarchy, giving priority to systems that were difficult to move, such as large ductwork and gravity plumbing lines. Later, during construction, the BIM focus shifted to 4D simulation. The coordinated 3D model was linked to the Primavera P6 schedule using Synchro. This helped the team study crane locations, concrete pour sequences, and just-in-time delivery for prefabricated components. The results were significant. The project recovered lost schedule time, reduced major field rework, improved site logistics, and was delivered on time and under budget. This case reinforces the main lesson of the chapter. BIM is most effective when the project team selects the right BIM use for the right phase. The strength of BIM does not come from using every tool at once. It comes from using BIM strategically to support real project decisions.